Hello everyone, welcome to DrZ Academy. In today's video, we're going to move on to the next section, moment generating function and probability generating function. Alright, so let's start. Firstly, let's consider this definition. Alright, so let x be a discrete random variable where let n be a positive integer. Alright, so then the nth moment of x is defined to be what? The expectation of x raised to the power n. That is, expectation of x to the power n, right? So that's what we have, the nth moment of x. Now, of course, now we will see that expectation of what? X is going to be the first moment, right? The first moment of x, right? And also we have expectation of x squared. That's going to be what? The second moment, right? And so on, right? So, and so on. Now, very good, right? So now let's consider this example. Let x be a discrete number with the following PMF, all right? So we want to find the first three moments of x. All right, let's do it. Okay, the first moment is going to be the expectation of x, right? So, which equals what? Summation x, p of x, right? So 0 times 0.15 plus 1 times 0.20 plus 2 times 0.40 plus 3 times 0.15 plus 4 times 0.10. Okay, so let's find this one here. So it's going to be 0.2 plus 0.8 plus 0.45 plus 0.4. Okay, so 1.85. Okay, so 1.85. That is the first moment. All right, so the second moment, our expectation of x squared equals summation x squared p of x. So equals 0 squared times 0.15 plus 1 squared times 0.20, 2 squared times 0.40 plus 3 squared times 0.15 plus 4 squared times 0.10. Alright, so let's do this. 0.2 plus 1.4 plus 9 times 0.15 plus 16.6. Alright, so I found this one is 4.75. Okay, so the third one, expectation of x cubed, is going to be summation x cubed p of x. Right, so again, 0 cubed times 0.15 plus 1 cubed times 0.20 plus 2 cubed times 0.40 plus 3 cubed times 4.15 plus 4 cubed times 0.10. So let's find this one. 0.2 plus 8, 3.2 plus 27 times 0.15 plus 64 times 1. Okay, all right, so I found this one is 13.85. That's it, right? So this is 3 moments. The first 3 moments, we found them, right? So basically by definition, yes? All right, so now let's introduce the moment generating functions. All right, so what is a moment generating function? So the moment generating function is sometimes we just write MGF. All right, so the moment generating function of a random variable x denoted by mxt is defined to be the following expectation. Okay, so it's a special expectation. What is that? All right, so it is given here, expected value of e to the power tx. All right, t times x. So which equals the summation over x t e to the power tx p of x, provided that the expectation exists for t in some neighborhood of 0. right, in some neighborhood of 0. Now, consider the following theorem. If, right, let mxt be the moment generating function of a random variable x, then we have the following equation. Okay, so it is what? The expectation of x to the power n. This is the nth moment. Remember, right? So this is the nth moment. Okay, so nth moment equals what? This is m, right? So the nth derivative of this function at point 0. The value of the nth derivative, nth order derivative of the moment generating function at point 0. Okay, so where what? This m and t is simply the nth order derivative at point t equal to 0. Alright, so that's why it is called moment generating function, right? So through this function, we can find the moments of the random variable. Okay, alright, so let's consider this example. Alright, so this is x be the discrete random variable with PMF, the same PMF as the previous example. Now, we want to find the moment generating function first and use it to generate the first 3 moments. Alright, so now let's consider the moment generating function. How to find mxt? Right, solution. Now, the moment, I'm going to the moment generating function of x is, alright, so mx of t, by definition, it is the expectation what? E to the power t capital X, right? So equals the summation over x, all right? So e to the power tx, all right? P of x. Now you can write down this one, right? So remember when x is 0, so e to the power 0t, all right? So which is going to be just a 1, right? So it's a 0.15, right? 1 times 1.15 plus when x is 1, so e to the power t times p of 0.2, right? Times 0.20 and e to the power 2t times 0.40 plus e to the power 3t times 0.15 and e to the power 4t times 0.10. So we can be rewritten as 0.15 plus 0.2 e to the power t plus 0.40 e to the power 2t plus 0.15 e to the power 3t and plus 0.1, right? 0 e to the power 4t. Now, of course, this one exists at the neighborhood of the neighborhood of 0, right? So that's the moment generating function of x. Now let's use this one to find out the moment generating function. So firstly, we need to find the first derivative. Okay, here it's x prime of t. Right, so find the first derivative. So what's the first derivative? This is going to go away, right? So and this one is going to be the same, stay the same. E to the power t plus, now using chain rule, so this is going to be what? 0.8 e to the power 2t, right? And plus, this one is 0.45 e to the power 3t, right? And finally plus what? 4.4 e to the power 4t. Okay, so that's the first derivative, right? And then you can find the second derivative by taking the derivative of the first derivative. Yes, so this is 0.2 e to the power t plus 1.6 e to the power 2t plus 3 times okay, so 1.35, is that right? Yes, I think so, right? So 1.35 e to the power 3t plus right? So for 1.6 e to the power 4t. Okay, so and then the third derivative of t, right, this is for x, equals 0.2 e to the power t plus 3.2 e to the power 2t plus, okay, let me just use the calculator. Okay, so is 3 times 1.35, okay, it's 4.05. 0.05 e to the power 3t and plus 6.4 e to the power 4t. Okay. All right, so that's going to be the first three derivatives for the moment generating function. Now we can see, all right, so the first moment, expectation of x equals what? M prime x, right? 0, right? When t equals 0. So this one equals what? Right? So when t equals 0, it's going to be just a 0.2 plus 0.8 plus 0.45, right? So it is going to be what? 1.45, yes? And the expectation of x squared is going to be the derivative of the function, the value of the second derivative at 0.0. So it is 0.2 plus 1.6 plus 1.35 plus 1.6. All right, so let's just do this in summation. 0.2 plus 1.6 plus 1.35 plus 1.6. Okay, 4.75. And finally, expectation of x cubed equals 3, right? So 0 upon 0 equals 0.2 plus 3.2 plus 4.05 plus 6.4, which equals 2 plus 5 plus 6.4. Okay. So 13.85. Okay, 13.85. All right, so now let's just consider this is the three moments, right? So we found these. Oh, okay, so did we make some errors here? Okay, so let's see. Okay, so I think I made some errors. 0.2 plus 0.8 plus, oh yeah, we forgot to add another one here, right? So 0.2 plus 0.4 plus, okay, another 0.4 here, and plus 0.4 here. So I didn't forget this one, right? So then it's going to be 1.85, right? So very good. All right, so just be very careful. All right, so, sorry. Okay, so there should be plus 0.4 there. So we got the same answer, right? It's 1.85, 4.75, 13.85. And if you compare that, it's exactly the same, right? So 1.85, 4.75, 13.85. Okay, so that's why, all right, we are using what? The moment generating function to get the first three moments. We got the same results, right? So that's why it is called moment generating function. Okay, very good. Now let's consider another example here, right? So let's clear. Sorry. Okay, let's consider this example. All right, so let x be the number of phone calls to the front desk of a hotel from 9 p.m. to 10 p.m. Assume the PMF of x is given below. All right, so now find the moment generating function mxt and use this mxt to find the expectation and the variance of x. All right, let's do this. All right, solution. Firstly, the moment generating function is expectation of e to the power tx, right? So, which again equals a summation over x all those value of x, right, e to the power tx times p of x, right, which is here, right? So 6 to the power x over x factorial e to the power negative 6. All right, so which again equals, let's just do this one, right? Summation x, right, e to 6. I'm going to put this one 6 e to the power t, all right, raised to power x, all right, here x factorial e to the power negative 6. All right, so what is this? What does this equal to, right? So you can see that this is e to the power negative 6 is a constant, right? You can take it to the front. Here x is from 0 to infinity, right? So this is basically e to the power what? 6 e to the power t, right? So which equals what? E, all right, 6 e to the power t minus 6, right? So that's going to be the moment generating function for this random variable. Yes? Okay, all right. So then we can see we want to find the expectation and variance. So how can we find that, right? So let's expectation is the first moment, and variance is what? Remember? Okay, so if you remember that variance of x equals the expectation of x squared, which is the second moment, right? Minus what? Expectation of x square of the expectation. Yes, so you see that if we can find the first moment, which is the expectation, and also the second moment, right? So we can just plug in the formula, find the variance, right? So now the next thing is to find the expectation and the second moment, first and second moment. Okay, so in order to do that, we need to figure out the first derivative, all right, of t. Okay, so which equals you can see that that's 6 e to the power t, all right, e to the power, okay, so 6 e to the power t minus 6. That's the first moment. All right, so the second moment is going to be what? A product rule, right? So this is a product now, okay? So, or you can just written this one as what? 6 e to the power 6 et plus t minus 6, right? In this way, it's going to be just another chain rule, right? So it's going to be the derivative on the top is 6 times in the parentheses 6 et plus 1, all right, in the e to the power 6 et plus t minus 6, right? That's the second derivative. Okay, so now then we from this one, all right, so we can find, all right, so the expectation of x is m prime at point 0 when t equal to 0. So it's what? 6 okay, so yes, that's right. Okay, so first derivative, yes, that's right. Okay, 6 e to the power. Now 6t when t equal to 0 on top is 0, right? So now e to the power 0 is going to be 6, right? And then expectation of x squared, all right, so equals the second derivative at point 0 is going to be what? 6 times, so 6 plus 1, right? So e to the power 0. So that's going to be what? 42. 6 times 7, 42, right? So therefore, the variance of x equals, right here, expectation square equals 42 minus the square of the expectation. 42 minus 36, that's again 6. Right, that's again 6. Okay, so we have the expectation is 6 and the variance is also 6. Right, using what? The moment generating function. Right, see, we firstly found the moment generating function and then use the moment generating function to find the first 2 moments. And the variance is simply using this formula. Yes? Alright, so very good. Okay, so here is a property of the moment generating function here. Alright, so let's consider this property. Okay, so this property. Okay, so linearity of moment generating function. Let mxt be the moment generating function of random variable x, then the moment generating function y of y equals ax plus b, where a is not 0 and b are constants. Right, so e is going to be the following: myt equals e to the power bt, mx at. Right, so this proof is pretty simple actually. So moment generating y is going to be expectation of e to the power. Right, so let me just write down here y of t equals t times y. Right, so this is going to be the same as e to the power ax plus b, right? So times t, because t times y, right? So then this one equals expectation of, right, e to the power bt times e to the power atx. Alright, so which equals, now e to the power bt is a constant, you can take it to the front. Alright, and times the expectation of e to the power atx. Right, so now if you will this one as a new variable, right, so it's something times x, the expectation of that is just what? E to the power, okay, so here we have e to the power pt and mx of at. Alright, so that's what we get. Alright, so that's basically the linearity of the moment generating function. Alright, so what is the moment generating function of a linear transformation of x? Right, so if we know the moment generating function, and then we have this one. Now let's consider this example. Suppose the moment generating function of x is given here. Find the moment generating functions of the following random variables. Alright, so it's basically just use the previous theorem, right? So y equals this one, so moment generating for y is going to be equals here a equals 2, b equals 1, right? So it's going to be e to the power bt, e to the power t times x of at, right? A is 2, so that's 2t. Okay, so e to the power t, mx 2t, so applying 2t here, so it's a 0.7 plus 0.3 times what? Instead of t times 2t, right? To the power 3, which is e to the power t. All right, so 0.7, 0.6t raised to power 3. Right, that's going to be the first one, right? Okay, now for the second one is also easy, right? So for the b here is a is what? -1/2, b is -1, right? So m y of t equals e to the power -t mx of -1/2 t, right? So equals e to the power -t in the parentheses is 0.7 plus, right, 0.3 times -1/2 t. Let's use a bracket here. Cube, right? So which equals what? E to the power -t, and this is 0.7. It's because minus, right? 0.15 t. 3. Okay, so that's going to be the moment generating function for y for the in part B, right? So basically we just used the theorem before. Okay, so very good. Now the next topic is going to be the probability generating functions. All right, so again, the probability generating function is to generate the probabilities. All right, moment generating function is to generate the moments. Okay, so now let's consider this one. Let x be a non-negative integer valued discrete random variable with pk is px equal to k is 0, 1, 2, then the probability generating function denoted by pxt is gonna be defined to be this one, right? E to the power t to the power x, right? T raised to the power x, right? So it's a summation from 0 to infinity t raised to the power x, p of x, so which equals this one, right? So that's what we have for pxt, the probability generating function. Okay, so consider the following theorem. All right, so let pxt be the probability generating function of a non-negative integer valued discrete random variable x with pk equals the probability x equal to xk. Then we have the following equation, right? The p of k is the case derivative of the probability generating function at point 0 over k factorial. Okay, so where this is the case derivative of pxt. Okay, so you can prove this one. It's pretty easy. Okay, it's pretty easy to prove. Okay, so you can prove this one. Okay, so I'm not going to do the proof, but you can just go here and do this derivative and find out this one, right? So it's pretty simple. All right, so now let's consider an example here, right? So the probability generated function of a non-negative integer valued discrete random variable x is given below, right? So we want to find the probability mass function, the moment generating function, and the expectation variance of x. Now let's consider the how to find the probability mass function, right? So that's the possible values of x, and also what? Their corresponding probabilities, yes? Okay, so solution. Okay, so we have, all right, so probability mass function. Now you need to find pxt, so you may want to find the derivative, right? And it's going to be what? 3 times what? T plus 2 over 3 raised to power 2 and times 1/3. Yes, so chain rule. Okay, so it's going to be simply what? T plus 2 over 3 square. Yes, so that's the first derivative. And then you can find second derivative, which is, right, 2 times, right, t plus 2 over 3 times what? 1/3, which is 2/3, right, times this one. So which is actually we can write down in one, right? So it's going to equals 9 to t plus 4. Okay, so that's going to be the second derivative, right? So it is 3 times 3, that's 9, right? So the third derivative is going to be what? Just 2 over 9, right? And then for all others in xt, it's going to be just all 0, right? So for n greater or equal than 4. Okay, so we have that, right? So now it's therefore what? P of k, P of, okay, let's say k. Let's use k instead. Okay, therefore P of P of 0, all right, equals what? That's just the px is 0. Okay, so let me just show you here. So P of 0 is just equal 0 factorial, right? So it's P0 is itself. Okay, so it's just a px of 0. Okay, so what's going on with this? Okay, so equals what? Hey, come on. Oh, sorry. Equals, when t equals 0, that's 2 over 3 to the power cube, that's 8 over 27, right? 8 over 27. So P of 1 is going to be px prime at 0.0 over 1 factorial. So it equals what? It's just a p prime equal to 1, right? So that's going to be when t equal to 1. So that's 4 over 9. All right. So and p of 2 is going to be px second derivative of 0 over 2 factorial, which equals, all right, so now it's 2 over 9, when t to 0, 4 over 9, 4 over 9 over 2, that's 2 over 9. Okay, that's 2 over 9. And then finally, that's p of 3 equals, all right, so px third derivative at 0.0 over 3 factorial equals, all right, so 2 over 9, so 1 over 9, yes? Is that 1 over 9? Oh, 27. 2, 3, 6, okay, 1 over 27. 1 over 27, I believe so, right? So 3, yes, that's right. So that's P of 4, P of 3, and for all others, k is going to be what? They're all 0, right? So it's going to be just a 0 for k greater or equal than 4, right? Greater or equal than 4. So therefore, the probability mass function is simply what? The possible values are, okay, x can be 0, 1, 2, and 3. And p of x is going to be what? This is 8 over 27, 4 over 9, 2 over 9, 1 over 27. All right, so that's basically the PMF. Right, so we got the PMF in part A, yes, using this probability generating function. This is part A. Now, for part B, we want to find the moment generating function for x. All right, so you can do that. Yes, we can do that. B, expectation, well, moment generating function, right? So it is a moment generating function. So it's m x of t equals, right, as we see that expectation e to the power tx, which equals summation x e to the power tx p of x, which equals, all right, which equals what? When t is 0, right? So when x is 0, that's going to be 0, 8 over 27 plus, all right, when x is 1, e to the power t, p of 1 is now 4 over 9 over 9 e to the power t plus, all right, and then when t equals 2, p of 2 is 2 over 9. So 2 over 9 e to the power 2t, and plus, all right, and finally is 1 over 27, right, e to the power what? 3t, right? 3t. Okay, so that's the moment generating function of x, right? So very easy. And for part C, right, so we want to find the expectation and variance. Now for this one, you can either use this table, right, or use the moment generating function, right? So either way works, right? So I'm not going to do that because it's pretty simple here, right? So I believe you can do this for the expectation and the variance, all right? Either way, you can use a moment generating function if you want to, or just by definition, right? So they are both very easy, okay? So I will leave that as an exercise for you, okay? All right, so I think that's pretty much of this video, and I really appreciate your time, and thank you very much for watching. So if you feel like this video is helpful, and please smash on that like button, and if you think this will benefit some of your friends, please feel free to share it with them, right? So as always, thank you very much, and I will see you in the next one. Bye bye.